Might be up to 5 people now. Now, if this thing is moving at a constant velocity, what do we call that state? For something moving at a constant velocity, what's happening?
Equilibrium.
That's the word right there. So equilibrium means that the velocity doesn't change. In other words, the change in velocity is 0. What are the other two things that it means? Well, what's dependent upon the change in velocity?
Acceleration.
Yes. So if change in velocity is 0, acceleration is 0.
And force is 0?
Total force. Yes, officially there are units.
I guess you just gotta ask us some questions to get it out of us.
All right. Now the reason I make sure that I throw the word total in there is that I've had a number of students write, there's no force acting on the object, when it's actually, there's several forces acting on it, they just balance each other out. So the total force is 0, that add up to 0. So if I pull this thing at a constant velocity, that means the total force is 0. So if we think about that, so I got a surface right here, I got my box, and I'm pulling on it. If we look at the dual force diagram, I have weight acting down, I have normal force acting up, I have my applied force out here, and then there's going to be friction acting back. So I'm making the claim, assuming I can pull it horizontally, and hopefully close enough. If the total force is 0, then the normal force and the weight happen to be equal, and my applied force should be equal to the friction. So I have a way of figuring out what the friction force is just by pulling on it at a constant velocity, which I'm going to try to do at a constant speed in a constant direction. And hopefully I'll get the right force scale that will work for this. That might be too little, but I'm going to try it anyway. There's conveniently a hook right here. That is a 5 Newton scale. 10 would probably be good. That's a 20. Take a 10. All right. Let's turn on the force inside. There we go. All right. That seem relatively constant?
Mm-hmm.
Yes. I'm trying to read this thing as I go. Get moving there, and it is hovering around just shy of 4 newtons. It's about 3.8 newtons. Did you want to do it?
No, I was getting into it.
No, that was not a criticism. It was just, you know, I'm doing this and telling you, and if one of you wanted to actually experience the joy of pulling something here. Oh, one thing I did forget. Because I was not getting the same result there, and I hate when that happens. But it's a physics demonstration, so what are the chances that it actually worked? That's about a little over 3.5 newtons right there. The other one's a little under 4 newtons. Obviously not the same thing. Not ideal what I was hoping to get right there, and I'll explain what I believe is the difference. But would you agree that that is roughly twice that? That area is twice that-ish?
Sure.
Actually, now I'm hungry. Ish. Got nails for it. that dream of having a demo one. There's a static electricity demonstration that works beautifully as long as everything's clean, but the more people that touch it, the more oils that get left behind, and suddenly it's horrible. All right. Please work. That's still hovering around 4. Yeah, that's better. And that's hovering around 4. So the reason surface area, trust the second one, ignore the first one. The reason why surface area doesn't really matter as much is that when there's greater surface area, that basically the weight is spread out over more area. There's more contact, there's more places for friction to occur, but there's less force between the two. And then when you turn on its side, the weight is more concentrated, but there's less involved, and it seems to balance each other out. There's this dual of how much force there is between them versus how much is affected. So surface area actually is minimal effect. I try to find research of someone who's actually done really high precision experiments with this, and it's very difficult to find.
Really?
I found a college senior who did a detailed experiment, and that's about it. Because once you get beyond this, you get beyond basically what we're doing here, you got something that's workable. And engineers have something that works, and they're good with that. Physicists don't deal with friction a whole lot because they're dealing with things too small for friction to really be an issue. Or so huge, you can ignore it. So you got this, but there's a group at NC State that's trying to study it in more detail, but they're doing a quantum physics look at it.
Was their results about the same as yours? Or did you get
So I haven't seen, the detailed experiment I saw was trying to find what's called the coefficient of friction, which we'll talk about in a moment. Yeah, it would be nice to actually find someone who's done a high precision experiment on this, as opposed to spring scales. So,
what if you pull it faster or slower?
the speed of the pull. So that last one was 4. It's still around 4. The trouble is because I'm slowing down because I'm running out of table there. Yeah, this will work. So that was 4 right there, and then slowly. Wow, that's huge. It still seems to be hovering around 4. My hand is sort of shaking and not doing this steady velocity. They can tell that because the thing is wiggling up and down. It's still around 4, again, high precision experiments. There have been some who've claimed that there is a subtle thing there, but it does not seem to be. Speed tends to affect air friction more, and we are, of course, ignoring air friction. All right, so surface area ultimately does not have an effect. Weight of the book. This is the trickier one. I am going to lump these together since they're so intricate, they're so tightly connected. All right, so imagine this book has a weight to it. If you don't believe it, you can come over and pick it up, and you will notice that there does seem to be some weight to it. And now, I put this on top. When I push on the book, do you think there's going to be more friction or less friction?
More friction.
Okay. But the weight of that book is not changed. there is more friction. It stopped a lot sooner. But it was not the weight of the initial book, because we didn't change the weight of the initial book. So the question is, what did change? Be careful about that.
The added mass.
All right.
Like the force that's pressing between the book and the table.
And what is that force called?
Gravity?
Ooh, normal? That's what it's called.
I was thinking about it because it doesn't have to be. When I said weight, I immediately thought there's friction too if you're like sliding something up or down a wall, and then weight would be different. So it's not that.
So even though everyday language we talk about, we added more weight to it. The book itself, that touching the table where the friction is existing, that is not, we're not changing the weight of that book, but we are changing how tightly they're pressed together. So one of the two major factors is normal force. However, there's another factor, and I sort of hinted at it as I was cleaning stuff over here. There's one other major factor.
You mentioned oil.
Other?
Oh, not a force, but
You mentioned oil from your hands.
therefore, what would be the other factor? Oil is a very specific thing in general. On what?
The table, the surface.
That's the word I was looking for there. The surfaces. So the other thing it depends upon is the surfaces. And if you don't believe it, if it ever ices again, it's much easier to walk on carpet than it is on ice, even if you're wearing the same shoes. The surfaces matter. So normal force, why? That's something we've talked about before. Surfaces, this is bundled up, and I made an allusion to it before, in what is known as the coefficient of friction. And the symbol used for it, because of course physicists don't want to write all that out, is the Greek letter mu. Mu. It looks like a U with a stem up front. So if you draw a U and just put a stem up front, here's your mu. And so now we get down to the two competing theories of friction. And I believe it's the late 1700s. Someone came up with a theory of friction, which basically we've been using ever since. At some point in the last few decades, there's been a challenge to that. Doesn't affect what is in the textbooks. Engineers have something that works, so they're not really too concerned with it. So I'm going to talk about what is known as it's what I call, no one else calls it this, the nook and cranny model. Not granny, but cranny model. So I got a table and I have something on it and that thing's going to slide. So a nook and cranny, if I zoom in on it, and we start looking at the surfaces, that the book might have a surface with, it's not smooth. There's the texture there. And the table has its surface. So we have these two surfaces here that are sort of competing against each other. Not competing. It's kind of like a jigsaw puzzle. If they got these pieces right here where some of them are starting to interlock. And it's very difficult to get this thing to move because they're interlocked. And if there's a greater normal force, that means they're shoved together even more and those parts are even more interlocked. Thus, greater the normal force, the more friction there is. Now, once you get it moving, you're basically either broken off pieces, in which case you've changed the surfaces, or you've basically popped it out of the interlocking piece and it's now sort of gliding across the top and it's easier to move. In this model, there are two different types of coefficient. There's the coefficient of static friction, thus the S. So coefficient of static friction. And this deals with how much, this is related to actually getting it to start moving. Static friction means it's not sliding. It wants to, but it's not sliding. And then there's the coefficient of kinetic friction. And kinetic means moving. And so once you get it moving, then it's easier to move. And I sort of saw that right here. It wasn't talking about that, but to get it moving, it required a little bit more force, but once I got it moving, it was relatively easy. In this model, if I look at so this would be friction and applied force. So the force required in order to get it to move. That the friction, the static friction, it's basically going to match it, it's going to match it, it's going to match it. So if I push it on this table right here, the table's not moving. So whatever force I'm pushing on the table, the friction's acting back and it's keeping it where it is. And it's going to keep building and building and building. That static friction is going to build up and build up and build up until I finally reach that breaking point, at which point it will start to move. So there's some maximum static here, which is labeled Fs max. And then once I get it moving, it's relatively easy. And so this would be the kinetic friction right here. So you push on it until you reach the breaking point, in which case the friction then drops off and it's easy to move. Related to that, mu sub k is less than mu sub s. Now in terms of what's a reasonable value for mu, I've never seen anything where mu's been bigger than 1. I'm willing to bet that some scientist somewhere has come up with a substance which does this, but I haven't seen it. Rubber on asphalt. I think it's somewhere around 0.7, somewhere in that region, just to give you some idea. Ice on ice, I think, is around 0.1. So when you have skid marks, when you're trying to figure out how fast a car was going based upon the skid marks, they'll have an actual official value for this, but they're basically using exactly what we're talking about right here. All right, questions so far on the Nook and Cranny model? All right, and now the attraction model. And the attraction model, if we do a zoom in right there, it's not the nooks and crannies that are really of importance, it's how close are the surfaces actually together. Because we have atoms down at this level, and those atoms are being attracted to other atoms. And so what you see here is there's an attraction between the two particles, or between the two objects. And the closer they are, the greater the normal force, the closer they are, the more attraction there is. And that's what it's overcoming. In this model, it is not an issue of reaching a breaking point and suddenly the friction drops off. In this model, we did friction and applied force. you get to a certain breaking point, at which point it starts to move. It's supposed to be a straight line there. And in this model, the static friction is equal to the kinetic friction, which is just equal to this coefficient of friction. It seems to me that there's a very clear difference between these two models and what's predicted. But the testing has so many errors that it's very difficult to differentiate between the two. I've seen evidence of both. I suspect the real answer is somewhere in between, which is a cop-out in my opinion, but that's what I got.
Wait, what would be evidence for the attraction model?
What was the evidence?
Yeah, I can't really imagine a way in which that would be.
So in that case right there, when I was pulling it, I clearly saw a drop-off. The place where, what are the chances this is going to work? All right, so right now, if this table is level, there's no friction acting on the box, but as soon as I tilt the table, there's now friction acting on it because the box wants to slide. And it wants to slide, it wants to slide. It's going to reach a certain point, and hopefully I'll catch it before it goes too far. It's going to reach a certain point when it's going to start, there we go.
I think if you jiggle it, it'll start moving. Like the table.
It will eventually go. I'm going to put it closer so I can reach it more easily. There we go. It's the fact that, all right, so it's obviously sliding like that. Still sliding, not sliding. I bring it back up, it's not sliding, bring it up a little bit more, still not sliding. So the fact that the actual angle at which it starts to slide ideally would be the same angle every time, but it's not. And so the argument for the attraction model is there's better than what I'm giving right now. But